Hello, everyone. I'm so pleased to be joining the second international conference on construction materials and structures. I would like to thank the conference organizers for giving me this distinct opportunity to talk to you today. I thought carefully about what should be the topic of my presentation. I considered to, discuss some of the ongoing research in my lab or the modeling work that some of my grad students are doing. And then I thought it's probably more urgent and impactful to touch base on the most pressing issue that the construction industry is facing today, and that is the issue of decarbonization of cement and concrete, and the entire issue around net zero construction, whether that's achievable, and what is being done to attain that aspirational goal. So in Canada, we have an aspirational vision to attain net zero, and we really aim at transitioning the Canadian economy to become cleaner, to become green. And that is perceived as an immediate priority, and therefore substantial efforts are needed by various sectors of the economy, the society, to get there. And this entire thing is driven by the main issue, and that is trying to avert the adverse effects of climate change. And therefore, the government of Canada has reacted to that by setting a net zero goal by year 2050. Now, what does it mean to reach net zero economy? So we could do that essentially in two ways. Either our economy has to emit no greenhouse gas emissions at all, which is obviously impossible, or we need to reduce emissions and offset those emissions through things like, planting more trees or employing technologies that can capture the carbon that we are generating before it goes into the atmosphere. So essentially, Canada is not alone in this. Canada has joined about 120 countries who have committed to a net zero objective by year 2050, including all the G7 nations and many others. Why that matters and whether that's attainable, specifically when we consider our industry, the cement and concrete and the construction, that is the focus of my talk today. So beyond that, by 2030, the Canadian government aims at reducing our carbon emissions by somewhere maybe around 40 to 40% below the 2005 levels. And that goal needs to be achieved by 2030. It's quite ambitious, but it has been published by the government in March 2022. So that process is ongoing. Why this is so critical? It is so fundamentally important because of the catastrophic environmental events that we have been experiencing in recent years. Wherever you are around the planet, you will be experiencing maybe severe droughts, floods, wildfires, and devastating hurricanes. In fact, I speak to you today, I'm joining you from Canada, and right now, around mid-December, today, we're experiencing frozen rain. It's very difficult to walk outside. It's very slippery. It's very difficult to drive. A couple of decades ago, I remember we would have, half a meter or more of snow, and now we have green grass. And so this is dramatically changing. And this has been inflicting, significant damages in terms of economic loss, human life loss, and major ecosystem disorders that are changing habitats and plantations and so on. It's emerging to become an existential threat to humanity. And this keeps being aggravated as we progress in the years, with these events becoming more frequent and more intensive and more negatively impactful. And this is bringing us really to the fundamental issue, trying to mitigate all the anthropogenic, greenhouse gas emissions from the various sectors of the economy. And, the numbers are there, there is growing consensus now. I mean, in 2020, we have about 1 degree Celsius higher temperature than what we experienced before the Industrial Revolution. And if nothing is done, that probably is going to reach 3 degrees Celsius by 2100. And that is going to inflict tremendous damage if nothing is being done. Climate scientists have been advising that we should not really exceed 1.5 degrees Celsius to avert these possible catastrophic environmental, social, and economic disturbances that could be resulting from climate change. And to be able to achieve those mitigative goals, we really need to urgently and rapidly and strictly lower, the carbon emissions from various sectors of the economy. So climate change has been a logical result of the development, population growth. We achieve now an extra billion on the planet Earth within the space of 10 years or maybe 12 years. And, it took the entire history until the Roman Empire to achieve like 250 million people. And now we achieve a whole billion within a decade. That brings need for schools, for housing, for buildings, for water treatment and waste management facilities, and so on. And therefore, a lot of development. And with developing countries trying to catch up on the developed countries, there is more demand for civil infrastructure. Combined with this is the obviously aging civil infrastructure and its replacement and its demand for new construction materials. And therefore, the manufacture of cement has outpaced many other materials around the world. So, in fact, to the extent that now the cement production, represents about 8% or so of all CO2 emitted around the world. And the numbers there are available, in the different literature. So you could look them, but they're pretty astonishing. With the specific case of China, for example, China has seen its cement production expanding 25 folds since 1950. Just between 2005 and 2013, there was more than 70% growth in cement production. The global cement production reached a whole 4.65 gigatons in 2016, and has been, swinging somewhere between 4 and 4.2 since then. And all the actions that we have been taking to reduce cement production or clinker production have not really succeeded. So it is a tremendous challenge worldwide. So we talked about China representing maybe half of all the worldwide cement production. India comes second, where you are with about maybe 7 to 8% of the global cement production. To just give you a benchmark, the entire European Union is maybe around 4 to 6% of the world cement production. So it is a tremendous challenge. And when we look at the worldwide distribution of cement production, you see most of it is actually happening in developing countries. Obviously, China is leading the pack with about half of the world production, and then followed by India. And then you see, most of the other, large producing countries are developing countries, including Iran, Vietnam, Brazil, Egypt, Turkey, and Russia. So essentially, the only couple of world developed countries that produce significant amounts of cement are the United States and Japan. So to the extent that if you consider the cement industry as a country, it would rank third after just China and the United States in terms of CO2 emissions. And while this is a tremendous challenge, it also represents a tremendous opportunity, because it is expected that the carbon dioxide CO2 market or utilization market will reach somewhere around $600 billion of value. So innovations and developments in this area would be very significant. So the concept of sustainable development has emerged around the issue of mitigating climate change and greening the economy and so on, and trying to attain sustainability. But the concept, while it's a concept that is revolutionary in nature, it is somewhat vague and difficult to grasp. It's not substantive. Engineers like to talk numbers, and sustainability and sustainable development don't come across as highly quantitative numbers. They are much related to policy making and so on, and therefore they remained ambiguous and led to maybe some failures in attaining our objectives in the pursuit of sustainability. And to translate it in more tangible terms, if we just follow the development of policies, so maybe the beginning of the entire sustainability discussion maybe started around 1972 with the UN Scientific Conference, also known as the First Earth Summit in Stockholm in June 1972, where we had the Declaration of Climate Change for the first time. It took maybe till 1987 for the UN General Assembly to adopt an environmental perspective called To the Year 2000 and Beyond, and which introduced the concept of sustainable development at that time in the policy agenda for the first time. And while it produced a very large document, it was rather disappointing because the whole thing was just a small, text at the end of the big document. In 1988, we saw the Intergovernmental Panel on Climate Change, known as IPCC, emerging. Was established for the first time in November 1988. And the Forum for Examination of Greenhouse Warming and Global Climate Change was established at that time. 1989 was really the year for climate change. It's a watershed year where we've seen a lot of things, declaration around climate change. Then there was the General Assembly identifying climate change as an urgent issue for the first time. There was a resolution that was emitted, and there was the Maldives Malay Declaration on Global Warming and Sea Level Rise, and the Helsinki Declaration on Protective Ozone, etc. The Montreal Protocol, that is more known than the previous policies that I have mentioned. 1990 was the World Climate Conference, and then 1992 was the Rio de Janeiro Assembly in Brazil, where we had the Rio Declaration, that is quite significant and ended up being signed by about 158 states committing to reducing emissions. Then there was the Berlin Mandate, 95, the Geneva, now we started calling them the conferences of the parties since 1995, was COP1 and then COP2 in Geneva, and then the Kyoto Protocol, which was COP3, which is probably the most significant so far in all of those agreements. And now, just last month, we had the COP27 in Sharm el-Sheikh in Egypt. There was a breakthrough agreement on a new loss and damage fund that was created for vulnerable countries. Now, with all these conventions, COP27, you would expect that we're achieving amazing results, right? Well, no, wrong. Because if you look at what we have achieved through all these conventions, if these conventions were pursuing rather an exponential growth in CO2 emissions, they would not have been more successful, right? If the policies started somewhere, here, and then you see this is the result of all the policies that we have been making. Why are we failing like this? Why we keep failing? You look at the growth in global air temperature and how the post-industrial, behavior that is growing exponentially. What are we waiting for to be successful in curbing these growths in temperature and greenhouse gas emissions? Looking closer to our own turf, the cement and concrete industry, and if you look at the cement-related CO2 emissions, in this color, how they are growing through the years, and then the cement production through black curve. We keep producing more cement, and more cement is generating more CO2. So the situation doesn't look really very, very promising. Although there have been some successes, some successes, and I will skip this slide to talk about some of them a bit later. But behind all of this, the policy making, what is the issue with this policy making? In my mind, it is the simplistic approach to trying to do policy making around climate change. Now, I took this picture from my little daughter's elementary school textbook, and this is how they represent, sustainability through this graph, a simplistic graph for small children. Now, you look at documents around circular economy and embodied carbon at a more advanced scale, and our representation is not that more sophisticated. What Buddy Richmond calls the laundry list thinking. This is the approach of the laundry list thinking. What is this approach? Is we base our policy making on mental models, and mental models are futile. They change within the same debate. The same person can tell you an opinion, and you talk with them 5 minutes, they change their mind because they're building the discussion on mental models that always finds a reason for something. So, for example, you could say the sales are bad because marketing is inadequate. And then you can say marketing is inadequate because the salespeople are not motivated. And then you can say the salespeople are not motivated because, and you can keep going because. That's not how systems work. Systems are more complicated. They are affected by time-dependent loops. They are non-linear in nature. They don't lend themselves to simplistic mental models. So the mental model thinking is, you're sitting on this end of the boat and you say, I am sure, God, that the whole isn't on our end, right? Because we're not capturing the big picture of the issue. Or the fragmented conceptualization of issues where, you don't see the link between this part of the system and that part of the system. Systems thinking is capable of capturing these things. And this is why in the title of my presentation, how we can go, towards from the laundry list thinking versus the systems thinking approach to things. So here's again the model of sustainable development that the textbook for my daughter has versus how systems thinking will represent the same model. Time-dependent loops feeding into each other in a complex system. It could be a system of systems. And therefore, for policy making, if we don't understand these interrelationships, the complexity of the problem, then the policy making issue will lead to the scenarios that we have seen on the previous slides. So what systems thinking? Systems thinking is a holistic way to investigate the factors and interactions that contribute to possible outcomes of a system. So you can model complex systems or systems of systems governed by feedbacks, by adaptive and counterintuitive behavior, and still you could get reliable outcomes. It sees the whole system and the patterns rather than the mental models that look at snapshots. It focuses on the interrelationships rather than the things. Take an example just to simplify this, and I won't spend a lot of time considering the time restraint I have on my presentation, and I see the time advancing, and I am still very early in my slides. So let's give an example to simplify this, to illustrate why we keep failing in policy making about curbing greenhouse gas emissions from cement and concrete. Let's say we have a traffic congestion issue somewhere. So the mental model, and the policy making in our governments and ministries, they will say, all right, let's build a nice highway. That's going to sure solve the problem. It takes a lot of investments, public money, and so on. Sure thing. We go there and build a very nice highway, and people are happy. Traffic becomes so beautiful, and then problem solved, right? No, wrong. You know why? Because now you get the feedback of the system coming in. People start getting attracted to that neighborhood, and businesses maybe also get attracted to that neighborhood. People will say, oh, it's nice actually to commute to that neighborhood. You know, I can buy my own car. And then, you know, you get more residents, more cars, more traffic, and so on. And in fact, the problem that you wanted to solve becomes a much more complex problem to solve now. And that is because we did not capture the system's approach to the issue. As opposed to that, system modeling will look into the feedbacks into the system and the exogenous variables and the interrelationships and the time-dependent feedbacks and the causal loop diagram to try to find a solution, something that looks like this. Or that congestion system dynamics model, you know, we have to look at it in a different way and develop policies that would be more robust in terms of capturing these complexities. So this whole thing is built around, you know, the field developed by Forrester at the MIT Sloan School of Management in the 1950s. So you hear me talking about systems thinking and system dynamics. Systems thinking is you know, something you can sketch on a piece of paper by focusing on the interrelationships, you know, and the causal loop diagram and so on. System dynamics is you take that system thinking into a computational, you know, framework and software like Stella or Vincent, where, you know, you translate the systems thinking causal loop diagram into you know, stocks and flows and a model that actually can predict or can simulate the behavior. So you know, there are different types of feedbacks and growth systems in a systems model, and I don't want to dwell into this too much, but to simplify this, you know, there is that feedback that needs to be captured. For example, you know, if you open a tap and you're filling a bucket and you're not getting feedback, you're going to flood the house, right? But your eye is providing with you feedback. So first it gives control to your hand to open the tap, and then it's getting feedback how the water is filling into the bucket and capturing the water level and information and so on, and then you can regulate things. So you know, there is some goal-seeking growth system like the S-curve, and sometimes, you know, it reaches a goal and then collapses. For example, you know, a population of bacteria, you know, it has food, keeps growing and growing rapidly, then it depletes that food and starts collapsing. Or sometimes you oscillate around a goal. So there is a lot to be learned, and then, you know, you build a system dynamics model using very simple components, the connectors, you know, that are represented by arrows in this diagram, and those, they establish essentially the relationships between the parts of the model. And then you see those stocks that are represented by the rectangles, and those are you know, accumulate physical or non-physical quantities. For example, what is the amount of cement produced at a certain time? And then you see the flows represented by something that looks like a tap, and those, you know, transport information and quantities. So for example, you know, the rate of cement consumption. And then you see the converters that are represented by those circles that you see here. Those are, for example, you know, to perform algebra or calculations. For example, what is the demand curve for cement? Anyways, using such simple tools, and you see these pluses and minuses in the model. When you see plus, it's a reinforcing behavior. For example, you have more self-esteem, you accomplish more. You have lower self-esteem, you accomplish less. That's a reinforcing behavior. The balancing, which is negative, is, for example, you know, the more you spend, the less money you have in the bank. So using simple concepts like these, we can model, for example, the effect of alkali activated materials on CO2 emissions, rather than somebody sitting, you know, and saying, you know, alkali activated materials are amazing, they reduce CO2 emissions. Well, it's not as simple as that. You need to look at multiple components of that system and how the feedback behavior and the effect of, you know, construction demolition waste, you know, natural resources availability, the precursors that we use, how available they are, the activators, the carbonation of concrete, etc., and try to build that into a system dynamics model that can predict the behavior in better reliability. And within that system that looks so simple, you can find sectors that are hidden there look simple, but in fact, a sector to calculate the carbonation, a sector to calculate the CO2 emissions, and so on, to build a system, or a sector for the composition of the alkali activated materials to capture the complexity of the system. So by that, we can do policy testing. And no, policy testing doesn't mean predicting, like on September 1st, 2061, our cement production is going to be this much. It's not like that. It's for testing policies. So systems modeling and system dynamics is really for testing policies, policy scenarios under certain assumption. So is the world population, is India's population going to grow, or grow and slow down, or is it going to grow and decrease? What's the economy perspective in the future? And so you test policies, and you see that depending on those policy hypotheses, things, the CO2 emissions can be quite significantly different. So it's not as simple as what the United Nations goals have been versus what was actually happening in the real world. So I will maybe end that discussion around the systems modeling there. We have published a few papers in different journals, a system dynamics model for sustainable cement and concrete, novel tool for policy analysis, that was published in the American Concrete Institute Materials Journal, and several others that you can find in the literature. I invite you to do more reading around this. Starting point would be Jay Forrester. He was an American computer engineer and systems scientist. He's perceived to be, the founder or the father of systems dynamics. And then Barry Richmond, who was a PhD student of Forrester. He's the former managing director of high performance systems. He's credited for taking, system dynamics from the academic world and making it into business, with the company that created the program Stella. And I think it's called Modeling Environments. And then John Sterman is still at the MIT. He's also a PhD graduate of Forrester, and he's the current director of MIT System Dynamics Group and MIT Sloan Sustainability Initiative. All right. So moving further, I would like to discuss with you briefly what is being done out there. We want to, we are very ambitious and we want to attain net zero, maybe better, maybe beyond net zero, maybe we could have a positive outcome for it. I mean, we could have infrastructure that captures carbon instead of producing it. So what are we doing? Is that goal achievable? What are the initiatives that are out there in the research and the development and the industry and the cement producers and so on? Are we getting there? Are we realistically getting to that goal of 2050 of attaining, net zero by 2050? Since we had so many countries signing to pursue that goal. So the first thing we'll discuss is the alternative clinker technologies. We'll abbreviate that as ACT. So we know that the production of 1 ton of clinker emits somewhere around maybe 0.83 tons of carbon. And a lot of this comes from the calcination of limestone. You got, limestone as the main, calcium carbonate as the main ingredient in cement production. And when it's calcinated into a cement kiln at high temperature, we get the calcium oxide that is the main ingredient in clinker, and then the CO2 gas that is emitted into the atmosphere. This is about maybe 60 to 65% of the carbon emissions of clinker production. The rest of it comes, from the mining of raw materials, and then, the energy used for heating, for firing the cement kiln, and so on and so forth. So what these technologies aim at is to achieve cement decarbonization, reducing essentially the carbon footprint of cement through different alternative technologies. One of the ways of doing this is to have clinkers that are functionally less dependent on calcium. If our clinkers need less calcium, then they would be releasing less CO2 in the atmosphere. So by doing this, well, it's not just about CO2, it's also about having a product that would have physical and mechanical properties that compare to the current ordinary Portland cement, yet would be emitting lower carbon, and they should also be compatible with our existing standards and existing production techniques so that they be economically viable and competitive for the real world industry to adopt them. And yet fulfilling such requirements that often come as conflicting is challenging, and therefore it still needs extensive laboratory and large-scale research studies. And one of the main reasons why I selected this topic today is that I wanna reach out to those young students and researchers in the audience, and those who our future generation of scholars and innovators to pursue these goals. We're facing a tremendous challenge that the previous generations have created, and now we need innovative solutions to get there. So some of the things that are being done, and I will survey these quickly, and you could always reach out to the pertinent literature and dig more into these things. I will start with one alternative clinker technology, the oil shale Portland clinker. So what is this? Essentially, we will be using shale that contains oil as an ingredient that we put in the kiln. So not only now we have the shale as an ingredient in the cement production, but we have that part of it that is energy, oil, that should be reducing the energy demand for cement production. So using, for example, 16% oil shale ash in ordinary Portland cement can reduce the clinkering temperature by approximately 10% without significant changes in the properties of the clinker. So it could be a pozzolanic material, and yet also providing energy for reducing cement production. There are low organic material, we call them calcareous oil shales, that have ratios of oxides compositions that is somewhat similar, in fact, similar to ordinary Portland cement, and those can replace maybe 3/4 of the raw materials when we manufacture belite cements. Belite cements. What are belite cements? Well, the cement components, and we will come to this a bit later maybe. Cement clinker has C2S, which is belite, C3S, which is a light, and then C3A, C4AF. So high belite cements, essentially, they contain a larger quantity of C2S. They would be rich in C2S. And C2S, unlike C3S, can be produced at lower calcination temperature and would probably lead to less CO2 emissions. Another alternative clinker technology is the reactive belite rich Portland cements. It somewhat relates to the topic I was discussing. So we said clinker would contain mainly dicalcium silicate, tricalcium silicate, tricalcium aluminate, and tetracalcium aluminoferrite. So this is the belite phase. So belite rich cements, usually around maybe 40%, because normally, belite is not that high in normal cements. You find C3S as a major ingredient, maybe because, as structural engineers, we're addicted to F prime C. We want to have the 28 days compressive strength, and therefore they give us cements rich in C3S to produce early strength, and they grind the cements finer, and so on. High belite cements, they would be somewhat different. I mean, they hydrate slower and so on because of that richness in C2S. But due to the processing temperature for high belite cements, they would consume less energy and they would be emitting less CO2. Maybe we can produce them somewhere at lower temperature, maybe 100 degrees Celsius, lower than the normal cements, and they don't require substantial changes in technology. I mean, we can produce them using the normal cement manufacturing, the existing basically technology. Similar or somewhat related to or along the same lines is the belite, yeelimite, ferrite, and calcium sulfoaluminate belite. And here essentially, essentially products similar to calcium sulfoaluminates. But to be able to produce these, we need cost-effective sources for the raw materials to be able to produce these more sustainable cement alternatives. So maybe as sources of alumina, we could resort to things like low calcium fly ash, marble and ceramic dust waste, residual bauxite, residual kaolinite clays, and so on and so forth. And as far as the sulfate sources go, maybe phosphogypsum, coal combustion residues. So this will depend on the local context and whether we have, an access to sustainable sources of raw materials to produce these kind of alternative clinker technologies. The carbonatable calcium silicate cement. Essentially, here we pursue the hardening of calcium silicate using accelerated carbonation. For example, using mineral wollastonite, we can rapidly cure it under CO2 under certain specific temperatures and relative humidities. For instance, in a precast plant, it would be conducive to produce such cement, and in a chamber that is ventilated using CO2, and which will allow to reduce maybe somewhere around 30% of carbon emissions compared to ordinary Portland cement production. There are some other emerging clinker technologies, and I probably don't have the time to dwell on all of them. Magnesium oxide, for example, derived from magnesium silicates. There are a number of patented magnesium hydrocarbonate cements out there that are actually able to sequester CO2 in their hydration products. Examples, for example, something called known as Solidia cement. It's patented. So essentially, it uses less calcium carbonate in its formulation. Its kiln temperature is lower. Instead of say 1450 Celsius, you would need somewhere around maybe 1200, and which is significant. It enables reductions maybe of carbon emissions by 1/3. In addition to this, the curing would be using CO2, and then maybe for 1,000 kilograms of binder, you could capture maybe 300 kilograms of CO2, which is very significant. And then there are other ones. For example, silightment, or it's a patented hydraulic binder. Here we synthesize, a precursor of calcium silicate hydrate that requires less energy, emits less CO2. And then there is the X clinker, but this is quite different. Essentially, here we need to it's quite a unique process, as we will need to essentially melt the ingredients in this process through pyroprocessing, and therefore even the entire technology of producing cement needs to be adaptable to that. When you melt the mixture, the existing technology may not be suitable to that. In addition to this, it requires higher temperature. So looking at these, I mentioned a bunch of things here that could be used for some sort of clinker or cement production. And the main difference between these essentially is what is their composition? What is their composition? So if you look at the terminology that I used earlier for all those different systems, this is ordinary Portland cement and some of the others that I mentioned in the discussion. And here you see the compositions, and you could recognize the alite, belite, aluminite, and so on, and some of the other phases. So the variability in these raw materials leads, the energy demand and leads the CO2 emissions that are associated. Most of these alternative cements, they don't unlike allied or C3S that is most responsible in ordinary Portland cement for CO2 emissions. They don't contain much of that. So yes, I mean, a lot of these technologies some come across as at their infancy or still lacking, technological advances or scientific research to maybe conduct life cycle analysis that is more robust to understand or evaluate the embodied carbon in such systems. Some other alternative technologies, instead of focusing on the raw materials, we focus, in addition to that, maybe, or in parallel to that, or in combination with that, on the alternative fuel technologies. Because, if you consider that the global average of CO2 emissions related to cement production is this number here, the fraction of CO2 from the calcination, essentially the chemical reaction of calcium carbonate giving you calcium oxide and then CO2, would represent maybe the majority, maybe 60 to 65%. And the rest of it, which is very significant, is actually related to the energy use. So alternative fuels, as opposed to the clinker alternatives that focus on these components, the alternative energy or sources or fuels will focus on these components and try to mitigate, which can lead to significant reductions in carbon emissions, sometimes reaching a quarter, maybe even more, depending on the technology that you would be using. Among the common ones, or the most known ones, is the use of biomass as fuels. Biomass essentially, could be from agricultural biomasses, for example. Agricultural products, they typically have a certain fixed amount of carbon, maybe about 45% or so, but they're perceived as neutral CO2 in essence, because they capture that CO2 through their growth. So what is the rationale behind perceiving them as a green source of energy? By resorting to such, biomass sustainable fuels, maybe we could reduce, the energy or the CO2 related to energy consumption of cement, maybe somewhere around 20% or so. And there are actually ongoing initiatives around this. For example, in Canada, we have a cement plant that initiated at 10% biomass in one of the plants here in the province where I am, actually in Ontario. And they use essentially, byproducts from plants, hemp, and some oat hulls and some other types of plants that are common in our area. And there are some others that use biomass alternative fuels around the world at levels up to 25%. So biomass and waste fuels, this may surprise you, but meat and bone meal. These used to be approved for feeding animals, but the European Union has banned that for health considerations, and therefore they resorted using those as energy source in cement production. They are actually quite common. They probably represent somewhere around 2 to 15% of the fuel used in cement plants around the world. Some places like Australia, they use them at substitution rates sometimes up to 40%, and they've been perceived as a best alternative fuel for cement industry. And then there is the sewage sludge byproducts of sewage treatment that could provide some minerals that could be useful in clinker production, but also a source of energy that reduces the amount of carbon-based fuels. And then there are the solid recovery fuels or fuel that is derived from the refuse, municipal solid waste, the used tires. So we have billions of used tires every year, and some other industrial oils and solvents and paint sludges. And although these actually provide effective uses or effective sources of energy for cement kilns and cement production, I think that we still need some research. We need to disclose, maybe substantiate in a more robust manner, in a more rigorous manner, what is their actual contribution to carbon emissions, and quantifying that, and coming up really with convincing figures, scientifically accurate figures as to how beneficial they are. More recently emerging and maybe more promising is the hydrogen fuel cells. For example, where I am here in Hamilton, Ontario, we have a steel producer actually resorting to hydrogen fuel. It's clean energy. It has the advantage of being able to be stored. If you produce energy from wind, for example, it's difficult to store. You can store it. It's renewable. It has zero emissions. It's very versatile and has quick recovery. In the specific context of cement production, we can use it in two different ways. One way is to provide thermal energy for clinker production. And the other alternative is actually to recover the heat from the cement kilns and use it for the hydrogen production. So it could be a two-way synergy right there. There is a potential to reduce maybe around 44% of CO2 emissions compared to, for example, when we're using coal. The other emerging solution around this is maybe the use of small modular nuclear reactors as sources of energy, maybe to help produce hydrogen as well. And all these things are being considered. Along with this is electrification. I'm sure you heard a lot about the electrification in cars and buses and so on. But in terms of cement production, the very high temperature that you need to attain using electrification is quite challenging. So there are some initiatives around that. For example, in Sweden, there is a NetZero project that aims at developing maybe a prototype for this. And there are different ways of doing, heat production using electrification. Maybe the microwave heating, plasma torches, flash calcination, electrical heating, and so on. I think this is an area for development in the future. It has not matured yet. Electric energy is challenging to produce. There are many sectors of the economy competing for it. So I'm looking forward to how this will develop in terms of cement production in the future. So alternative cement technologies, maybe the lowest hanging fruit in the whole system is really to replace the clinker with something, using minerals, industrial wastes, agricultural wastes. And this is something not new. We have been doing this. The challenge is that the conventional, materials that we used for this, for example, the slag, the ground granulated blast furnace slag. We are experiencing here in Canada, for example, steel producers switching from using, fuels for producing steel to electrification and hydrogen. And the slags they would be using now, they are no longer useful as pozzolanic or hydraulic materials for cement. Same thing for fly ash. I mean, in Canada, we no longer produce fly ash because we discontinued using coal as a source of producing energy due to the sheer environmental impact of combustion of coal. And we switched in favor of green sources of energy centered around, renewable energy from wind, from solar, and from biomass, and so on. So we're experiencing shortages of those traditional materials, slag and fly ash, and therefore one of the thrusts of research now is to look for alternatives to these materials, what we call supplementary cementitious materials. So a common practice in the current industry now, and I'm sure you heard about it in your neighborhood too, is the Portland limestone cement. It's not something new. This has been used since the 1980s. It was debated quite a long within ASTM, as some members perceived this as adulteration, they called it. They didn't want to accept it until more recently. Now we can use, PLC cements maybe containing somewhere around 10, most commonly 10% of limestone, could be up to 20%. In the European standard, they have a cement that maybe could contain all the way maybe around 35% of ground limestone. The earlier studies were rather focusing on the mechanical and durability features of Portland limestone cements, and later on came the perception that it actually saves CO2 emissions as well, and therefore there is more interest now in using these types of cements for sustainability purposes. The use of limestone in cement could be beneficiated much more significantly when coupled with supplementary cementitious materials, most notably with calcinated clays. And you probably, I'm sure you heard about the LC3 cement and the work of Karen Scrivener in Switzerland around this, and many other researchers, where we could replace maybe 50% of ordinary Portland cement clinker, maybe something around maybe 30% of calcinated clay, 15% limestone, and maybe 5% gypsum, and attain engineering properties that are quite comparable to ordinary Portland cement, and allowing us to maybe reduce, depending on the composition, maybe somewhere around 25% to 40%, maybe even 50% of CO2 emissions while maintaining excellent mechanical and durability performances. With this emerged the idea of clinker-free binders. Are we able to produce from wastes and byproducts, binders that could do the trick, be equivalent to Portland cement, ordinary Portland cement, and yet without all these problems that are associated with Portland cement, the CO2 emissions, and so on? There is ongoing attempts on this. Some more recent studies are gradually demonstrating that we can use waste materials only to produce hydraulic binders, and we're watching how that develops. The benefits of this is not only lowering the carbon emissions, but also the whole issue around the circular economy and the ability to valorize, beneficiate, give added value to some of the industrial wastes that are filling, our landfills, and which is a significant issue. So in this, we can use things like municipal solid waste incineration byproducts. There have been significant work around these initiatives. There are some studies out there. Not much evidence around the CO2 emission reductions or quantifying the carbon emissions related to this, but around the technological use of the material, and this is an area of further exploration. Similar to that would be the industrial solid wastes. Here we're talking things like carbide slag, the phosphogypsum, the sponge iron, cement kiln dust, paper pulp wastes, and other things that could be beneficiated in the production of binders for construction. Some of those binders could be hydraulic, some of them could be non-hydraulic, maybe based on carbonation or some sort of chemical activation to attain, engineering properties that are suitable for construction. There are the agricultural wastes as well, and there have been significant work around these for developing agro-cements and bio-inspired systems and so on. And we're all familiar with the use of rice husk ash and sugarcane bagasse ash and sawdust ash and corn cob ash and many others. I haven't seen the development of clinker-free binders based on the agricultural solid wastes yet, but I think there are some claims or recent claims that for the feasibility of this, and again, this is probably still at its infancy. And then there is the whole issue around carbon capture, utilization, and storage. This is probably the, while economically not so competitive, but it's promising and probably inevitable long-term solution. This is like a fundamental solution that we may end up, finding that is the way to go forward. So if we want to meet the net zero goal by 2050, I think carbon capture, utilization, and storage can help us go a long way in that direction. There are initiatives, ongoing initiatives around this. For example, there is a cement plant in Colorado, in the United States, that aims to operate a pilot technology with the CO2 capture of around 2 million tons per year, which is quite significant. So there is a huge potential around this technology, and there are some pilot projects and initiatives from multiple users. So carbon sequestration is one thing, but the carbon use can go hand in hand. So integrating the carbon sequestration into concrete curing can be also part of the decarbonization strategy. So the easiest way is probably to use it in the carbon curing of precast concrete, being simpler and easier because it's conducted in a controlled environment. The carbonation of recycled concrete aggregates, the sequestration of carbon in magnesium oxide binders, and the mineralization, maybe using the carbon along with some chemical solution that will produce things like, for example, aggregates or things like that. Dissolution of CO2, at least partly in the concrete, mixing water, and some other various potential applications. Some of them may emerge as innovations that probably we haven't thought about yet. So there are multiple technologies that mainly pivot around the advancements in the binder system, which partially or entirely replaces the system that is carbon intensive that we are very familiar with, along with the waste valorization technologies that are coupled with this, aiming at reducing the carbon emissions. The most common thing that we know is the use of supplementary cementitious materials. We're all very familiar with this. So I would not want to dwell a lot on the use of the diverse supplementary cementitious materials that we have explored over the last decades. The main challenge that we're facing is really the economic and sustainable availability of those materials and the need for emerging solutions and alternatives around those. I would not finish this topic without talking about the alkali activated materials. And there is a lot of literature around this. And I see my time running pretty quick, so I've got to be very, very fast in covering them. So the issue with alkali activated materials is that the activators themselves can be carbon intensive, and the need for sustainable precursors in terms of raw materials, but also effective activators that would be not carbon intensive. And the whole issue around recycled concrete aggregates from demolition and the aging construction, and the use of recycled aggregate concrete, as aggregate or maybe as a powder for cement manufacturing. For the specific context of India to close, there have been investigations of about 22 energy efficient measures for reducing CO2 emissions. There is potential, if everything is combined and optimized, to reach somewhere maybe around the 60 or maybe 68% in CO2 emissions in the Indian cement industry context. And therefore, maybe if my major goal in this presentation is to encourage all the researchers in your community, because India is a major producer. I mean, the problem of CO2 emissions from cement is a global problem, but the solution is local. And therefore, we need to explore what is most successful in the local context. So to conclude, our strategies and policies around climate change have by and large failed, and they have failed miserably through the policies of the United Nations, essentially because those mitigative strategies that we see around end up to be greenwashing policies just for talking, but the impact walking the walk and doing implementing the technologies and the innovations and the commitments around sustainability are not there yet. The problem is emerging into an existential threat to humanity, and we can no longer afford just to watch silently. And therefore, among several of the technologies that I explored here, there is a lot of potential for us to think about how can we immediately and urgently work towards greening the cement and concrete industry, lowering the energy consumption of buildings, lowering the embodied carbon of the buildings that we are building, and embedding the sustainability and the durability into the conceptual design of everything we do in our business for the benefit of humanity. Is net zero cement and concrete achievable? It depends. We need breakthrough technologies. We need a global vision and a lot of local effective solutions. We need to mobilize multiple solutions simultaneously. It's not a single solution. It's going to be many, many solutions working in tandem. We need large volume solutions. We produce a lot of cement and concrete, and the solutions we have to develop, they should be large scale. We need systems thinking. The fragmented thinking is not going to cut it. We need to think about the system of systems around this to develop the effective policies. We need a true commitment to sustainability, not just greenwashing. We need to be innovative in our designs, and we need our standards to follow the innovation and implement it. And now we have the potential of artificial intelligence and machine learning and the capabilities it offers to us to implement such innovations. That's my time. Thank you very much. It has been a pleasure to be part of this event. I thank you very much. I look forward to, meeting some of you in person. I am from McMaster University. This is our campus. We sit on one of the largest freshwater lakes, very close to the Niagara Falls, the famous Niagara Falls. Come visit. With that, I thank you very much for your attention. It has been a pleasure to be part of this event. And I wish you, Happy New Year coming soon, and best wishes. And again, really appreciate your invitation to be one of the plenary speakers in this event. And thank you so much.